All right, in this chapter we're going to be talking about sets and Venn diagrams. One of the first things that you need to be aware of is exactly what is a set. It's a group or a collection of numbers or objects. For example, if you wanted to notate the set of all vowels, you would use a capital letter and brackets along with the equal sign. And then you would put each member or term within this set. You would separate those by commas. So we have A, E, I, O, and U. Now if I wanted to notate the number of elements or terms, members in this set, I would put a lowercase n, and I would count these numbers up, or letters, excuse me, and this is the number of elements within the set. So we have two ways that we can refer to each of these letters. We can refer to them as elements. We can also refer to them as members. Either one of those will work. Now, if I wanted to specify whether or not the vowel A is a member of the set of vowels, then I would write the symbol for a member, and I would say A is a member of set A. And this would be the proper way to notate that. If I had an empty set, then I would notate it with an empty set of brackets, or I could put a 0 with a slash through it, and this would be an empty set. I have several different types of specific number sets. The first one is the set of natural numbers, or counting numbers, which looks like this. And it is an infinite set because it continues on forever. I also have the set of integers. Integers is another name for a whole number, and this includes 0, because 0 is a whole number. It includes positive and negative 1, positive negative 2, positive negative 3, and so on. Again, this is an infinite set. So we have infinite, and we also have finite sets. Again, infinite continues on forever, and a finite has a definite stopping point. Now, if I want to get more specific, I could talk about the set of all positive integers, which would not include 0 because it's neither positive nor negative, but it would include positive 1, positive 2, positive 3. Again, it's infinite, continues on forever. I also have negative integers. Again, this does not include 0 because 0 is neutral, but it includes negative 1, negative 2, negative 3, and it's infinite as well. A few more sets we have. We have notated with this Q symbol. This is the set of rational numbers. And a rational number is any number that can be written in fractional form P over Q, where Q, or the denominator, is not equal to 0. So some good examples of rational numbers would be the number 4, because I can write this as a fraction, and the denominator, or Q, is not equal to 0. That's rational. 1/3 would be rational. It's fractional form, and the denominator is not 0. If I had a repeating decimal, such as this, excuse me, not a repeating decimal, an infinite decimal that has no pattern, this would be called an irrational number. Since it does not have an end, I cannot write it in the form P over Q. Now, if it does, and we'll talk more about this later, but if it does repeat, like 1.3, even if it goes on forever, this is considered a rational number. So root 2, this is going to be irrational, because if you put this in your calculator, it's going to be an infinite decimal without a pattern. So this is irrational. Root 4, however, would translate as 2, and this is going to be a rational number because I can write it as a fraction, and the denominator is not 0. The last few sets we have the set of real numbers notated with an R as such. And this is any number that can be put on a number line. So take your pick. Could be 0, positive negative 1, 1.3, negative 2.5, repeating. These are all real numbers. If you put it on a number line, it would just include any possible number. And just like with integers, you can notate positive real numbers. Okay, on a number line, it would look like this. And then we also have negative real numbers. And it would, on a number line, look like this.